So my name is Chris Adams, and as Dan mentioned, I spoke here 2 years ago at another hotel, so I'm sort of a MedTech Monday alumni. So Ceeable is a digital health company, and we're developing a virtual reality device to detect and diagnose eye disease. So as you all know, eye disease is a large market across the world. There are almost 300 million people worldwide with various stages of eye disease. It's also a market that's growing or projected to double within the next 5 years based on the aging population, so it fits in that demographic. The current standard of care costs approximately $20,000 to $30,000. It has some issues, and I'll go over those. And then there's a problem of access, not so much in the major cities, but in the countryside and certainly in developing countries. So our device intends to fix that problem. So on the left-hand, on your right-hand side, left-hand side, is the current standard of care. It's made by Zeiss Corporation. Everybody knows Zeiss. It's a large medical device company. It is a box that's the size of a small refrigerator. It weighs approximately 100 pounds. Costs between $20,000 to $30,000 depending upon the components you add to it. And it must be placed in an isolated room with lights off and a dedicated space in the clinician's office. As you all know, clinician's office space is very, very precious. That's what we got there. So 2 years ago or so, we were working on developing a tablet-based version of that perimetry device. And the tablet-based version of the device intended to fix some of those problems. So this is a case where a startup moved in one direction. We developed a tablet-based device, we commercialized it. It's been used on thousands of patients across the world, but it had one issue. It works by the patient looking at the screen. There's a pattern on the screen, and the patient interacts with the screen with their finger. They essentially trace patterns or copy patterns that are on the screen. It turns out that our core demographic, which is say between 55 and 85, some of those 70-year-olds have a hard time with their mobility and their ability to reach out to a screen and trace the pattern accurately. So we found that out in the marketplace, and we found that some technicians were holding the hands of the patient, some clinicians didn't like it, and so we said, how can we fix that problem? And it just turns out that the virtual reality devices that are just coming onto the market were starting to proliferate. And so we said, there's our answer. So in this case, the pattern is in the device itself. So instead of the patient reaching out to the screen and tracing the pattern that the computer generates, you now take the virtual reality device, you place it over your eyes. The only instruction for the patient is to follow the flashing light. The computer then begins a series of flashes, and the patient follows the light. This is all instinctive. As you know, if I flash the light in front of your eyes, you would follow automatically. So in that sense, it becomes objective and instinctive. It's actually a much better test. It turns out that some of the patients who use the Humphrey Visual Field device made by Zeiss, they tend to fall asleep because they have to interact with it. They're in a dark room. Again, these are 70-plus-year-old people. They're in a dark room. The instruction is when you see a light, you push a button. The clinician knows that the patient's asleep when they stop pushing buttons, and it's been 5 minutes or so. So this is how the test process works. Essentially, you get a prompt that the test is going to start in a few seconds, and then the larger flash here, the larger spot on the screen is what the computer generates, and then the small dot is where your eye goes to. So there's eye tracking in the virtual reality device, so the machine is following your eyes as it's looking at the spot that's being generated. So on this next slide, we have a video. If you can just execute the video. So that large spot is where the computer generated, and the small spot is where your eye follows. And it's coming up. So it starts, so now you're looking at the device, it gives you the countdown, and then it starts to give you a flash, and that small dot is where your eye goes to. And so the computer is now recording your ability to recognize the flash and then to track the flash. And this goes on for 2 to 3 minutes, and it's 2 to 3 minutes per eye, and then it goes to the next screen. And so when you're done, we give you a map. So these dots represent areas of visual recognition, and then based on the score, we can tell you if you have macular degeneration, glaucoma, or some other kind of retinopathy. And this is just a little geeky slide I like to put up. Essentially, this is a trace. So if you look at the top left-hand corner, we'll give you a flash, a series of flashes, and I'll go all the way down to the bottom. This is the path that your eye is taking as we change flash locations across the screen. So this is a tracing pattern. And so the ability to tell you not only did you see the flash, but how long it took you to recognize the next flash, and then the process that you took or the path that you took to go to the flash. This is data that hasn't been available before in current devices. So we have all this in the background. So the advantages are obvious. That 100-pound device that has to be in a specific location, in a darkened room, we eliminate that completely. You can take and put on the VR goggles in this room, you can put it on in the closet, you can put it on in some rooms in the clinic, and it costs a fraction of what that large device costs. And then we have this whole digital data part of the technology. So once all that's done, we have a back-end patient management, clinic management system that was developed for the tablet, so we were able to repurpose that whole infrastructure, and this is all housed in the cloud on Amazon Web Services. So if you are a clinician, you can just log on, you can input your clinic name, you can input the patient name, and then the data is automatically imported into that patient file. And then if you look at the series of bars there, we can do progression monitoring. So we can say in January 1st, 2018, this was the first test, and then January 1st, 2019, after a series of 5 or 6 tests, these are changes that occurred. And so what we've also noticed over time is that these diseases have characteristic profiles, and this is where the big data applications come from. So you can see here on glaucoma, where you have a nice spike in the middle, where you have maintained central vision, but the periphery is flat. So this patient has lost peripheral vision capability. If you go down to the bottom, you have macular degeneration, you see the opposite that happens, where you have a missing central vision, and these people essentially have blind spots in their central visual field. So I could see the outline of the person, but I couldn't see the person's face, for example, unless I moved position. So these patterns tend to repeat over and over again, and we will be able to diagnose and make some clinical judgments based on the patterns themselves. And on the left-hand side is normal, where you have a flat plateau where the patient can see both centrally and peripherally. So the market is pretty vast worldwide. As I mentioned before, there are about 20 million patients in the US alone. You go double that for Europe and the other developed countries, and then for the developing countries, it's in the hundreds of millions. So our go-to-market strategy, which is nice in this business, because in the ophthalmology world, it's really a focused clinical application process, where you have approximately 2,000 retina specialists, 16,000 ophthalmologists, about 45,000 optometrists. And then, of course, the very large market, which is the consumer market. We envision not only selling to the practitioners, but selling to patients who want to monitor their progression at home, where we can then tie in the patient's device to the clinician, and every time a patient does a test, it goes into their clinical file, And if we set alerts and parameters, if they exceed that, an alert comes to both the patient and the doctor, and they can pick up the phone and say, I need to make an appointment. Very simple. We have contract sales forces that we're starting to work with, and the good news from the payer perspective is that there are CPT codes already in place for this kind of technology and for these tests. The typical test right now is reimbursed at the rate of $60 to $85 per test. You actually could not walk into an ophthalmologist's office, offer this technology, and if you didn't have a CPT code, they wouldn't talk to you any further. So the team is myself. I am a serial entrepreneur. I've developed technologies in the ophthalmology world. One of the technologies I developed is a contact lens-like device that heals corneal scars. My colleague John Servin is our software VP, and the inventor of this technology from Caltech is Dr. Wolfgang Fink. He and I met some time ago. And then our clinical advisors on here are Cynthia Matosian and Dr. Isan Sadri, who actually is local. So in short, we have a number of collaborators ranging from the National Eye Institute to Caltech, to Harvard Medical School, and NASA. Actually, NASA funded some of the technology. We have a disruptive technology. It is lightweight, mobile, and digital, and we think it's going to displace some of the legacy machines. Thank you.